and thank you for the introduction. My name is Tarek Elgohary. As Justin highlighted, I'm an assistant professor at the MAE department, and my research is in astrodynamics, space, and robotics. So a quick overview about my lab, if I can switch slides, yes. We do research in three main areas. The area of astrodynamics, which we'll be highlighting this afternoon, mostly concerned with space-based space surveillance systems and accurate uncertainty propagation for the space domain awareness type applications. The space portion is have some collaborations with the physics department on understanding the dynamics of lunar dust, charged lunar dust to be more specific. And the final piece, which is related to robotics, or generally controls optimal guidance, real-time optimal guidance, and robotics experience. Now, the common denominator in all of that is my background in nonlinear dynamics, control theory, and computation methods. So this is why we do what we do. Today, the talk will be mostly about the astrodynamics portion of my research, and that is related to the Cislunar Space Surveillance Network. So, as you might have heard, Space Force, NASA, Capstone, there's a lot of activity that is going to be happening in the space between the Earth and the Moon. The space between the Earth and the Moon, sometimes they call it ex-geo, or sometimes it's also called a cislunar space. This space is quite vast. The dynamics of that space are very challenging. Obviously, from basic orbital mechanics, we know that things around Earth orbits in ellipses or circles. Things are more or less well behaved. Most of the uncertainty comes from, if you're close enough to the Earth atmosphere in low Earth orbit, comes from drag or the atmospheric or some external perturbations that were not modeled, but we're pretty good at modeling the Earth environment in general. Beyond Earth, this gets you in what is known as the circular restricted three-body problem, or the three-body problem in general. And this dynamically, that could be a chaotic system. Another area is that the space is very large. We're talking about thousands of times larger than the space between Earth and the furthest orbit from Earth, which is the geosynchronous or geostationary orbit. So the magnitude and the volume of space is quite large. It's also of interest to various players, governments. Obviously, the area or the orbits around the Moon are of interest to commercial space, people who wants to land stuff on the Moon, the Gateway, obviously by NASA, and so on and so forth. So there is a lot of interest from NASA, from the DoD, from various places to understand cislunar space and to provide surveillance in cislunar space. The problem with cislunar space, because of the distances, because of the limitations of Earth observing what we call ground stations, telescopes, and such, the capability is not there. We don't have the capability to cover this. So the direction is to go for space-based space surveillance. Now, the history of that, we have a few missions in orbit that did SBSS, the space-based space surveillance about the Earth orbit. They are singular missions, mostly to test the concept. The Space Force, I think in 2026, is sending something called SHIPS, or Oracle, which is SHIPS stood for Cislunar Highway Patrol System, essentially another observer to monitor cislunar space, and they're trying to understand how can we monitor that space, where to place things, and so on. Also, there is a NASA mission called Capstone, where it's in a lunar orbit, and they also try to measure relative relative distances between two satellites to provide navigation information. So we are in the very early stages of efforts to understand that environment, and obviously, you know, the usual DoD type concerns of this is a vast space, we don't monitor it, and the Moon is of interest to many players, whether government or non-government. So the work that we have been working on, and these are pieces of various funding sources, is that the space surveillance network, obviously one observer cannot do the trick. So we're thinking of a multi-observer architecture or model. The second thing we want to answer is where to place those observers, where to place those satellites. We're talking about space that is thousands of times larger than our Earth orbiting satellite, and we really don't have a good way to optimize things in Earth orbit, believe it or not. It has been studied quite well for Earth coverage, so ground track, looking towards Earth. But if you want to flip the observer or to flip the camera and look towards the black background of space, things get a little bit less deterministic. Finally, how to compute uncertainties, how to make decisions in this environment rapidly. Various limitations we were discussing earlier related to hardware on satellites, and also the delays in communication and all kinds of stuff due to the distances that would affect these problems. So very quickly, the observation model that we have been studying and showed pretty good results. What we look at here is the Earth-Moon system, obviously not drawn to scale, but just to highlight things. This zero here is where what we know the rotating frame or the barycenter frame. So this system, all of this system rotates about this zero frame. This is our inertial frame. To give you an indication, and I'll show you that in the next slide, but these distances are tens of thousands of kilometers away from each other. So the idea is to place, let's say this is very not accurate, like this is just a cartoon, but we're going to place several observers to look at a certain target in that domain, in the Earth-Moon system. And the fact that everything here in that system is subject to that environment, to that dynamical environment. We're using a very simple idea that it's almost high school math, essentially, that you look at several planes intersecting between different observers, and those planes construct lines, and you intersect those lines, you start constructing points. And this point is the target. Now, we use, obviously, real data, not real data, like observational data, angles, measured from various observers to create line of sight measurements. Now the fancy words come in play. And once we have line of sight measurements, we start doing some cross products to get the normals to these planes, and we intersect them accordingly to construct what you see downstairs here as our measurement model. Now the measurement model is a function of each observer. You have some matrices that gets inverted. And here on the right-hand side, here you have the unknown target position in this measurement model. Now, this measurement model could be fed into a filter, any types of filters, the basic ones, the fancy ones, whatever filtering scheme you would prefer. But to show the power of this simple, very simple idea, this high school math idea or high school geometry idea, is this example. Here we're looking at a few things. So we're looking at, and this gives you also an idea of the distances in cislunar space. So this thing is the moon. We have an observer on the surface of the moon. We have another observer in a DRO orbit, which is called the distant retrograde orbit, the blue orbit. We have another observer in an NRHO, a near rectilinear halo orbit, which is this guy. And then we're trying to observe this dotted line. We're trying to estimate this dotted line, which is in a 9-2 NRHO. This is an unstable halo orbit, also a near rectilinear halo orbit. And this is called L2. This is a Lagrangian point. And this is, you can see that the scale of the distances here, we're talking tens of thousands of kilometers between things here. So what we're looking at is a previously divergent case. If you want to find an estimate or track this orbit, you will not be able to do that with angles only measure. You will have to include angular rate measure. And here we're showing, just by using kinematics, not even including the dynamics, we're able to get tens of kilometers of accuracy in from the barycenter, from the inertial frame that we highlighted previously, which means that in percent error, this is almost zero, because everything is measured about 40,000 kilometers away from that system. So this is very promising. One of the areas that we're researching, a couple of areas that we're researching beyond this is, can we take measurements in an asynchronous fashion? Can we include different types of measurements beyond angles only, like rates, angular rates, range rates, and any other types of measurements out there? And the promising structure here allows for that. And also, we are trying to define what would construct a bad measurement, how do we do the estimation process accurately, and various other sub-areas of that estimation process, or tracking an orbit in Cislunar. The second thrust of this work, and this is still this is an NASA-funded effort, is that we are looking at the optimization of these of the locations of these satellites. So obviously, in this previous example, if I have something that is in this dotted line orbit, then yes, I can put something here, I can put something there, I can maybe put something in L2, and intuitively think that, oh yeah, I can cover this orbit quite well with these 3 or 4 observers. But we want to, the idea is we want to define coverage, not just as a function of location, but also as a function of the sensor profile. Some sensor in space-based space surveillance have very narrow field of view, like a rectangular beam, but they have a very long range. And some sensors look like these circles down there. They're called omnidirectional sensors. They look everywhere. Obviously, this is not realistic. This is very academic. You cannot have a sensor that looks everywhere. You have to do some attitude maneuvers to cover a 360 degree. But this is an assumption downstairs here that has been used in these types of coverage simulations. So efforts before this included these sort of geometric intersections, and no dynamical constraints have been looked at, no sensor constraints have been looked at, and more importantly, no specific coverage requirements have been looked at. So I might not be interested in covering all this dual band. I might be interested in covering, so this is in a plane, these are, this dual band is the orbit or the area of the orbits that I'm interested in. I might be interested in covering a certain volume of this area as an area of or a volume or a space of interest. So we're looking into this. We're using a computer science concept for octrees, essentially going down the tree for defining how the fidelity of looking at these areas or these volumes. And we've started this work this year, and we're still developing these concepts. Future areas or future work in this area would include how to do the inverse problem. So now we're doing coverage. Now that I can quantify coverage very accurately to the nth level, I can essentially start looking at the inverse problem. If I want coverage, how many sensors, what are their characteristics, where to put them, and so on and so forth. And this would be very useful in something like Cislunar, because although these look like orbits, but really there are some crazy stuff that can go here. I'm bringing like a very nice, well-behaved orbit or set of orbits here, but some, like one orbit that we're looking at is called the 2-1 orbit. It goes all the way back from the moon to the Earth, orbits Earth twice, go all the way to L1, which is another 20,000 kilometers away from Earth, and come back to the moon. So that's also a cislunar orbit. So some orbits are really, really intense. So coverage of these types of things would require that level of analysis that does not exist right now. The final part is related to how do we, now that we have these coverage and we have these, how do we do predictions? How can predictions be done? And for that, we're using some computational techniques that does uncertainty prediction, that does uncertainty quantification. Essentially, even with the best coverage, with the most optimized coverage, there will be coverage gaps. And with that, I have to propagate from the last point, from the last known point, to the next time where I pick up the object of interest. And between that, I have to also propagate the uncertainties of that object. Now, in different fields, uncertainty propagation is dealt with differently. In astrodynamics, we have to go to very, very high fidelity approximations. We have to go beyond 3 sigma all the way to 6 sigma, because usually we compute probability of collisions at 1 in 100,000 chance. And if this happens, there is an alert that goes off from Space Force to an operator telling them you need to maneuver your satellite, even if it is that low of a probability. So this is why accuracy is very, very paramount. Obviously, we're talking about a lot of money out there.